In this module, we're going to talk about what's called internal energy, and well, actually in the first law of thermodynamics too. All right, so let's look at the first law of thermodynamics. It says that you can neither create nor destroy energy, although you can convert it from one form to another. And what we're going to talk about is internal energy. What that is, for any system, the internal energy of that system, it's just a sum of all the kinetic and potential energies of the particles that make up that system, the atoms and the molecules that make it up. Now, that's a lot of things to take into account. It's literally impossible for us to take even a simple system like a beaker of water and go through and measure and add up the kinetic and potential energies of all those atoms in there. But luckily for us, we have another way of getting at it. We can look at the change in internal energy of a system by looking at, by using the first law of thermodynamics, which says that energy can be neither created nor destroyed, which means that the total of the change in energy of the system and the surroundings must add up to zero. So if we know, measure the change in energy of the surroundings by putting a thermometer there or something, we know what the change in energy of the system was. And while we don't know the initial and the final states, we know the change in energy, which means we know how much energy, internal energy, went into or out of that system. And that's really useful to know. For example, now you don't have to memorize any of this right here in yellow, but, well, this you should memorize. But for example, in this chemical reaction, it ends up that the change in internal energy is minus 576 kilojoules per mole. And the way we interpret that as the difference in the internal energy of the products minus the internal energies of the reactants. The change was negative 576, and the negative means that it was released, that the internal energies of the products are lower than the internal energy of the reactants. And that energy went somewhere, went to the surroundings. Now, there's two means by which internal energy can be transferred into or out of a system. And that's by transferring thermal energy, heating it up or cooling it down, or having work done on or by the system. There's different kinds of work. We're going to look at one specific kind of work here in just a moment. But memorize this equation here, delta E, the change in internal energy of a system is equal to Q plus W. Q means the thermal energy transferred into or out of the system, and W means the work done on or by the system. Now, the signs are really important here. If Q is positive, that means that thermal energy is going into the system. We say we're adding heat to it, or we're heating it up. If Q is negative, then the system is releasing thermal energy. Now, from our point of view, if Q is negative, the system's losing energy, but to us it feels hot because we feel that energy coming out. And if it's positive, it feels cold to us because it's pulling energy out from our hands or whatever's touching it. Now, with work, a positive value for W means work's being done on the system. The system is gaining energy by having work done on it. If it's negative, that means the system is doing work and it's losing energy. So memorize this. Now, the kind of work we're going to deal with here is called PV work, or pressure volume work. And now, to look at where this comes from, we're going to look at a few definitions. Work, W, it's defined as a force applied over a distance. But if we look at what pressure is a force over an area. So if we rearrange just a little bit, we get force is equal to pressure times area. And if we replace force in this equation with pressure times area, we get work is equal to pressure times area. Now, the distance, okay, if what we're looking at is a cylinder, which is what we're going to start out by looking at here, then the distance that a piston in a cylinder, like this little disc right here is like a piston, right? It's moving up and down, or it can move up and down when a pressure is applied to it. Now, the distance it moves is delta H, so that's the D. And so now what we have is the work done on or by the system is equal to the external pressure outside of it times the surface area on top of this piston here times the change in height. Now the negative comes here because if this is being compressed, if the final volume is less than the initial volume, then our delta H is negative. But when you press on the system, when you compress it, you're adding energy to it, you're doing work on it. So we want our sign for W to be positive if our delta H is negative. So we put this little negative sign in here, and we end up with the expression that you should memorize, that work is equal to negative pressure times delta V, change of volume, negative P delta V. Now, remember state functions? Internal energy is one of those, but the things that the way energy can be transferred into or out of a system are not. Q and W are not state functions. Now, so delta equals Q plus W. So if we look at this system, if it's losing energy, if it's releasing heat, then Q is negative, and if at the same time it's expanding, then W is also negative, and we get negative change in internal energy. Now, if we add thermal energy, heat to us, and press down on it at the same time, then Q is positive and W is positive and delta E is positive. But we can have any two combinations of Q and W here. We could have Q negative, W positive, and then the delta E, the sign of delta E depends upon the relative magnitudes of Q and W. In this case, if Q is negative, W is positive. If Q is bigger than W, delta E will be negative, and vice versa. All right, so now let's look at a little example. We want to calculate the change in internal energy of a system if it releases 7.14 kilojoules of heat and has 5.25 kilojoules of work done on it. So first of all, releases, that means negative. Heat is thermal energy, that's Q. Work is W, and done on the system means W is positive. So we get delta equals Q plus W. Q is negative 7.14, W is positive 5.25, and we get negative 1.89 kilojoules. So in this particular case, the system's releasing 1.89 kilojoules of energy overall. It's gaining 5.25 kilojoules by being compressed, having work done on it, but it's releasing more than that, 7.14 kilojoules of energy by loss of heat or thermal energy. Let's look at another example. Let's calculate the work, just the work now, not the internal energy change, associated with the compression of a gas from 59 liters to 11 liters at a constant external pressure of 25 atmospheres. So up here, before we start this is a really important conversion for these kind of calculations, so make sure you memorize it. One unit of energy would be liters atmospheres. The relationship between liters atmospheres and joules is 1 liter atmosphere is equal to 101.3 joules. Now that's not exact, but it's 4 sig figs for you. All right, so we want to calculate the work. It's negative P delta V. The P is constant. It's 25 atmospheres. Delta V, it's final minus initial volume. So final is 11, initial is 59 from 2. And so we get positive, because the negative and the negative here cancel, positive 1.2 times 10 to the third liters atmospheres, converting it to joules and then kilojoules. We get 120 kilojoules. Positive means that it gained that much energy, the system did. Let's look at another example. Let's say we have a balloon, all right? A big balloon, right? And it starts out at 3.14 times 10 to the fifth liters and expands to 5.19 times 10 to the fifth liters by gaining 2.19 times 10 to the seventh joules of thermal energy. So we're heating it up, like a hot air balloon. We want to calculate the change in internal energy for this process at a constant external pressure of about 1.1 atmospheres. So delta E is equal to Q plus W. Q, it's just the change in thermal energy. It's positive because it's being added, so 2.19 times 10 to the seventh joules. Work is negative P delta V. Delta V is final minus initial, which is positive 2.05 times 10 to the fifth liters. So the work is negative P delta V, which is this number right here, converting it to joules by multiplying by 101.3 joules per liter in atmosphere. We get a negative 2.284 times 10 to the seventh joules. So it's doing that much work, but it's gaining this much thermal energy. So the delta U is Q plus W, so Q plus negative 2.28 times 10 to the seventh gives a negative 9 times 10 to the fifth joules. So it's releasing negative 9 times 10 to the fifth joules during this overall process.